All right, this is the first in our lessons on energy use in the body, and we're going to start with metabolism, which is the sum of all the chemical reactions it takes to sustain life. And these reactions require energy, and that energy allows work to be done. So let's explore the relationship between energy and work for a second. Energy is the capacity to do work. We're going to discuss two forms, potential and kinetic. And work involves applied force and distance traveled. Physicists have lots of formulas to explain these relationships between energy and work, but that's beyond the scope of our course. And finally, we'll look at power. Power is the rate of doing work, or the rate of using energy. So why do people care about metabolism, and why should you care about these relationships between energy and work and power? Well, it's because of the more work you do, or the more energy you consume, and that's why people exercise to lose weight. So the more work you do, the more energy you consume. So if you lower your calorie intake or if you increase your energy expenditure, you will lose weight. So let's look now, take a closer look at potential and kinetic energy. Put simply, kinetic energy is the energy of movement, and potential energy is resting objects with the capacity for work in the future. So here we have an object with a high potential energy, and as it begins to swing, it moves to kinetic energy, and that kinetic energy can be transferred back into potential energy. Remembering that kinetic is the energy of moving. The primary form of kinetic energy that biologists are concerned with are electromagnetic. And so specifically, we're going to be looking at the visible spectrum, that's the light we see, and we'll look at thermal energy, so think of heat. And then light and heat, those are our kinetic forms. The form of potential energy we'll concern ourselves with is chemical. So that, for us, is the energy stored in bonds, especially in organic molecules. But gravitational, mechanical, and nuclear energy are potential forms too. And so here you can see this potential energy could be converted to kinetic energy, heat and light again. So you all should have seen my demo with the pennies. As I held the pennies up in the air, that potential energy, specifically we were looking at gravitational, was stored in the pennies, and when I tipped the bowl over, that energy was converted to sound and motion. So that brings us to the first law of thermodynamics, that energy can undergo conversions, but it cannot be created or destroyed. Energy in living systems tends to end up as heat through metabolism. You probably remember this. You see the 10% rule, and that states that 90% of energy is lost to heat, and that heat is created by metabolic work as you move from one trophic level to the next. Lucky for us, the sun provides a constant supply of kinetic energy back to the earth, and photosynthesis can capture that energy. So here you see the equation for photosynthesis. Light coming in can power the synthesis of glucose. And then there is a corresponding process to take that glucose and release energy, and that process is cellular respiration, and the energy released will be transferred to ATP, chemical energy, and heat. So let's go back to the pennies. What did I cheer as the pennies crashed to the floor? That's right, I cheered entropy. That's all related to the second law of thermodynamics, that things tend to move towards maximum entropy or disorder or chaos, depending on how you like to look at it. I always like to think of a dog left to its own devices when its owner's away. Okay, now this dog, not too destructive. There's some chaos. That's better. All right, that is going to take some energy to restore that room of chaos back to order. And so things tend towards entropy. Now, energy conversion is inefficient. and entropy is unavoidable. And so we see this also in living things. When you look at cellular respiration, a single glucose could create many CO2 and H2O molecules. And those reactions are exergonic. They're going to release energy. And so that energy is also released as ATP and heat. Now, let's continue on with that. Let's look specifically at those exergonic reactions. So exergonic reactions release energy, and as they release energy, the products they create tend to be more stable and lower in potential energy. That would be something like the firework you see here. On the flip side, endergonic reactions absorb energy, creating high energy products. And so you can see the comparison here. And endergonic reactions are often known as biosynthetic and anabolic. Now when you look at this diagram, you see that exergonic reactions must absorb some energy. That energy is called activation energy before forming products, even though the products are lower in energy overall. Endergonic reactions do this as well. So this was an exergonic reaction. Here you see an endergonic reaction, and you can also see the activation energy required. That energy often comes in the forms of collisions or heat. And those forms of energy, again, collisions and heat, that's right, they're kinetic energy. Now there's a cool thing going on here. As an exergonic reaction is taking place, the energy it releases could power an endergonic reaction, and this is called reaction coupling. In our bodies, it involves a middleman, and that is the ever so humble and abundant ATP molecule. So let's focus on ATP some more. ATP is short for adenosine triphosphate. So the adenosine triphosphate molecule you see here, adenosine is an adenine specifically, and a ribose, so there's your adenosine, and then the 3 phosphate groups make your ATP. Now, you have an adenine, a ribose, and phosphates. Can you recognize the macromolecule you see here? I want you to think about that. ATP will carry the energy from an exergonic reaction to an endergonic reaction. Endergonic reactions we've looked at so far are things like sodium-potassium pumps, other things, motor proteins, other transport proteins, so the sodium-potassium pump is one of those. And then we'll talk more about chemical work that's done by phosphorylation. So ATP is constantly regenerated from an ADP and an inorganic phosphate. So here you see the ATP-ADP cycle, and the amount of potential energy that goes in is approximately equal to the amount that goes out. So it's a really, really efficient system. And how is this system so marvelously efficient? Well, when you're looking at the ATP molecule, you have 3 negative phosphate groups very, very close together, lots and lots of negative charges. It's unstable. They want to repel each other, kind of like, the 3 siblings that all got crushed in the back seat, maybe with the family dog. They're not really happy that close together. So, by adding a water, you have your hydrolysis reaction, and you can break that bond, leaving behind an ADP and an inorganic phosphate. The last thing I want to discuss before we move into our discussion of enzymes is catabolic and anabolic reactions. So catabolic reactions involve breaking down large molecules to form smaller ones while energy is released. And that is, by definition, cellular respiration. It includes cellular respiration. And that does create ATP. So we have our catabolic process. Anabolic pathways are used to build complex energy-rich molecules, and photosynthesis is our most common biological example of a biosynthetic pathway or an anabolic reaction. All of these reactions in our body rely on enzymes, and so this graph demonstrates the addition of an enzyme. And you can see that enzymes, which are the catalysts of living things, they do what all catalysts do. They lower the activation energy. And so you can see the difference here between the original activation energy without the enzyme and the lowered activation energy with an enzyme. And just like your car would have an easier time getting over a small hill than a large hill, this reaction will proceed forward much easier and faster in the presence of an enzyme. So here's how an enzyme works. When reactants, which we're going to call substrates, bind to the active site of an enzyme, the enzyme changes conformation. And conformation, we're talking about its shape. And the slight shifts in shape can put tension on the bonds that need to be broken, and they can help align molecules that need to bond. And once bonds have broken and formed, the products are released from the enzyme. And the enzyme can return to its original conformation and end up helping that reaction with new substrates over and over and over again. Now, enzymes can often run reactions in both directions. So if that product were to build up in concentration, the product could be broken down by the enzyme. So the reactant and product ratio does factor into the speed and direction of reversible reactions. If left alone, a single reversible enzyme could bring a reactant and product into chemical equilibrium where the rate of the forward reaction is going to be equal to the rate of the reverse reaction. So there still may be more of, say, here you see them as the green product. There still might be more of that than the red and blue C and D molecules, but the rate that we're moving through the first set of reactions on the top here would be equal to the rate that we're breaking things down. So here again is one more thing. So often there isn't a chance for enzymes to work in both directions in a single reaction because that enzyme is a part of a metabolic pathway. So enzyme 1 is consuming, and reaction 1 is consuming molecule A, and then reaction 2 consumes molecule B, and then reaction 3 consumes molecule C. And so they're driving the reaction through this pathway of enzymes and ending up with one abundant product. And so I want you to think, at the end, yes, we're left with the product, but what else is still present? So let's do a little review of the features of enzymes. Number 1, they speed up the rate of reactions, and that is very, very lucky for us because our reactions keep us alive. That's our metabolism. They're not consumed. They can be reversible. And they're very highly specific to the substrates that they react with. There's some other factors that influence reaction rate, especially in the presence of enzymes, and so that is temperature, pH, substrate concentration, coenzymes, cofactors, inhibitors, and regulators. And we're going to look at all of those in a little bit more detail. Oh, and remember that substrate, when we're talking about substrates and enzymes, we're talking about the reactant of the chemical reaction. So here you see the optimal temperature ranges of 2 different enzymes. Taking proteins out of their optimal temperature range can denature them, and that makes them increasingly ineffective as they become more and more denatured. But there are enzymes out there in organisms, such as the Taq polymerase that we use in some of our biotech processes, that comes from a bacteria called Thermus aquaticus, and that can withstand temperatures up to 95 degrees Celsius, and it has an optimal range of 75 to 80 degrees, like you see here in the graph. Humans, again, we take this to our advantage, and use those enzymes, or specifically that Taq polymerase, in some of our processes, especially in a process called PCR, which we'll learn later. Here you see optimal pH ranges for two enzymes, and so these enzymes could be suited to different parts of your body, and so they behave optimally when your pH is regulated according to body system. And so you're looking at optimal ranges for both of these, temperature and pH, but I want you to think about why are the curves shaped differently for the optimal temperature versus the optimal pH. Substrate concentration, I always think about this as a group of, young children, let's say second graders, and there's a whole lot of them, and they are just eagerly awaiting. It's Valentine's. They're going to make their Valentine's holiday cards, and there's only so much paper to go around, and so there's very, very scarce paper. And as you give more paper to the class, maybe you go from just having it at the front of the room to scattering it about on all their desks. They make those Valentines faster and faster and faster because they have abundant amounts of substrate, the paper, to react with. And this is the same way that enzymes operate in your body. When there is abundant reactant around, it's more likely that an enzyme is going to come into contact with those substrates. Coenzymes and cofactors are required for some enzymes to function, and they speed up the rate of others. And so here you're looking at coenzymes. They are organic, and you're seeing the oxidized form of one, and here it is in its reduced form. So NADP, or NAD, is a nucleic acid, and so it's organic, and it's a coenzyme, and its role is to transfer electrons. So the oxidized form can accept the electrons, and the reduced form can donate them. Here you're looking at ferredoxin, and iron ions are required to make this enzyme function properly, and so it's the cofactor here. Iron is also required by hemoglobin and catalase. It's a metal ion, and most cofactors are made of metal ions. Alright, finally, let's look at inhibitors. So there's a few different types of inhibitors. You can have competitive inhibitors, which move right into the active site and block the substrate from binding. You can have allosteric inhibitors, which bind away from the active site. Here in this picture, they're calling it non-competitive because, again, the binding takes place outside of the active site, but another term for that is allosteric inhibition. So let's focus in a little bit more on those allosteric interactions. So here you're seeing the inhibitor. So when the allosteric inhibitor binds, it changes the shape of the active site and will not allow the substrate to bind. But on the flip side, it can also activate, where when the allosteric activator binds, this enzyme can bind the substrate, and so it can run the reaction. So essentially, it turns the enzyme on. And finally, my final note I want to make about inhibition is that inhibition combined with a metabolic pathway can be utilized by living organisms to control entire metabolic processes. So this allows for negative feedback. And negative feedback is when the product is present in high concentrations, it will inhibit the process by shutting off the first enzyme. This is a type of negative feedback because the process itself is shutting down once it's accomplished its task. For this, I want you to think of something like an air conditioner or a heater. It shuts off once the desired temperature is achieved. In an organism, these feedback inhibition loops help maintain homeostasis. And isn't it great to be a living thing? We are so complex. And so hopefully the next time you're having a bad day, at least you can be happy that your body can fight the entropy of our universe with anabolic processes that are catalyzed by enzymes that work within negative feedback loops. Until next time, bye.